All right, so the recording has started. Good morning and welcome, my online academy chemistry students. I am, of course, Mr. Deitch, happily your chemistry teacher. Before we begin today's lesson, just a brief just some brief info to let you know. Our next live lesson will be on Friday. This lesson is going to be mostly for you to ask questions about the week's work. So that includes, atomic theory, nuclear, half-lives, all of that in preparation for the quiz, which will also be released on Friday. Your weekly assignment groups are on the Google Sheets that says who you're working with. The groups are a little larger for this one because there's a decent amount to do. I do not recall if I warned you about this one, so I'm going to warn you now. The build an atom is best done if all of you do the first section by yourselves and then collaborate on the rest of the sections. Now, only one of you has to type the final document, but you should all try to actually manipulate the animation to learn the material, to learn how it works, and to see how it is. It's a great resource. It's a fantastic tool to play around with how an atom is actually built, and that's kind of like the point of this week. So do what you will with it. I am starting to, grades are coming. You'll start to see more and more. Warning letters for work are coming as well. I will discuss policy changes on Friday for group work, but that's Friday. Today, our main event is we are going to talk about how radiation can be used. If you kept up with this class as you are supposed to, you have already learned what types of radiation there are, alpha, beta, gamma, and neutron being the four that we are going to discuss primarily. Now, it's not the only types of radiation, but those are the types of nuclear radiation that we are going to focus on. All right, so first we're going to go over how this radiation can be used, and then we're going to really delve deeper into one of the most important uses when it comes to a niche field. So first off, with this, nuclear bombardment is when we smack a particle into another. This could be an alpha particle, a proton, or a neutron, or even a whole nother atom, like a complete atom, even a big atom. We can use this to smash into something else and make a new nucleus. Many times when it makes a new nucleus, this nucleus will become unstable. So I don't know if this is actually going to load. I'm unclear if Teams is going to behave when it comes to that. No, it didn't. That's okay. So as that was, let's see if I can at least scroll back. Are you gonna let me do that? No, you're not gonna let me do that? Okay, sure, cool. We can do this many ways. Let me grab this and see if I can use this instead. Haha, I can. Okay, so basically what it is, if you can see this animation, if you download it and see, the little, the neutron smacks into this, causing the thing to break apart. Oh, if I occasionally look to the side and seem to listen, that's because today's school picture day, so they're constantly announcing people to be called, and I have to spend at least a little attention to make sure it's not, like an announcement that actually, matters a lot for what I'm doing. Number slide, this is on the PowerPoint. If you have the PowerPoint that you downloaded, this is, oh shoot, this is the old one. I think it's slide 87. I'm going to go with my gut saying 87 while the full PowerPoint loads on my computer. So I'm pretty certain it's 87. Let's find out if I was right. Yep, we started at 87. Okay, cool. All right, so so at this point we're at 88. So again, the one piece smacks into the other. Oh, no problem, Ariana. Thank you for using the chat. Remember, feel free to communicate with me. It's best if this is a two-way street. But hey, if you just want to sit there and listen to me and completely ignore what I'm doing, that's all on you. I'm just here to try to help you out. So why is Teams being weird now? It's now giving me a circly thing saying it's thinking. Well, hopefully Teams will think quicker because I've got stuff to do. So in any case, so the neutron smacks into it, destabilizes it, and it pops. This releases a lot of energy. and this is one of the major nuclear processes, is nuclear bombardment. Radioactive decay, which I believe was earlier, is another one. I think that was part of yesterday's. This is another one of the big ones. Again, it can destabilize the nucleus. Now, when the products of a reaction cause another reaction to occur, even if it is the same reaction, we call this a chain reaction. A chain reaction does indeed perpetuate itself. And we're going to talk about another term that goes along with it. So it just goes on and on and on. This is like my favorite picture. I mean, I really thank Mr. Doyle for making this because it really goes over how this is most effective. As you can see here, the neutron smacks into a U-235 and it splits apart into barium 141 and krypton 92. But oh, sorry, that's not going to work. Okay. So I'm just trying to get my pen tool to work. There we go. All right. So in any case, so this neutron is going to smack into the uranium-235. This is then going to break into barium and into krypton. Now, many of them, as will it allow me to draw? You should allow me to draw. Okay. I'm trying to see how teams. I mean, it's kind of funny to think about this because this is Microsoft products working with Microsoft products. So it's kind of like interesting to see what works and what doesn't work. And yeah, this is not working as well as I'd like. Okay, that's fine. I'll just use my mouse. So the neutron smacks into the U-235 and causes the reaction to happen again because it releases 3 different neutrons. But the reason I like this picture beyond a lot of the other ones is it shows you something that also is extremely likely to happen, and that's a neutron that just kind of flies off into nowhere. See, the thing with any reaction is there has to be some sort of connection. And if there's no connection, if there's no thing where they, hit, they touch, then, that's it. It's not going to happen. So I like this picture because it shows that some of them don't perpetuate, some of them just fly off into the void and really don't have anything that works, that affects. So then we've got 2 types of nuclear power that we use. The first one is fission. This was discovered first. A large nucleus is split. So fission is about splitting and it releases lots of energy. We use this in all modern nuclear reactors and the very old atomic bombs, like the ones that were dropped on Hiroshima and Nagasaki. Fusion is when 2 small nuclei are combined into 1 large nucleus, and it releases a lot of energy. You'll see this in the sun and in the more modern hydrogen bombs. Now, for anybody who does any research on nuclear bombs, the hydrogen bombs are scary powerful. And the Bikini Atoll story is a really interesting one. The U.S. government used to test these explosives by dropping them in places like, the Nevada desert and whatnot. But people got really annoyed that they were dropping nuclear bombs on American soil, thus irradiating it for a bit of time. So they started dropping them on islands. And one of the famous stories is they had a new bomb they wanted to drop on an island. And just like they've done a lot of times, they went to the island, they talked to the people who live there, and were like, yo, we are going to pay for you to have a vacation to the mainland. And we're going to drop a bomb on like the other side of the island, which is far away from where you guys live. And just to see how it is, see what it works. And we're going to record it. And so that okay? You all want a paid vacation? The story varies whether they said yes or they were encouraged to say yes, but either way, they went on their vacation. The U.S. set up a fake town and then dropped their brand new shiny bomb on that town. Unfortunately, that was a hydrogen bomb and not an A-bomb. So not only did it blow up the fake village, but it was so big that it also blew up the forest in between the two, and it blew up the village. And it actually blew up the entire island. It vaporized the island and countless gallons of seawater. It erased it off the map completely. So the devastating power of modern nuclear devices is terrifying. It is absolutely terrifying. It can erase islands. It can change the map. So Fusion is powerful. It's very powerful. In fact, it is what goes on in the sun. Sun's just a giant fusion reaction, and that is fueling pretty much all life on this planet and energy to every other planet in the solar system. So fusion's a huge deal, which is why we're trying to make our own fusion power. So far, it hasn't worked. More on that later. Fission again is splitting, and you can see these graphics. You've got the neutron bombards into the uranium-235, causing it to become 236, which is unstable. 236 naturally breaks apart into krypton-92 and barium-141. Both of these are radioactive waste. Krypton is a radioactive gas. Barium is a radioactive. It winds up being a sludge because it gets superheated, but it's mostly a solid, and it spits out those 3 neutrons that we talked about earlier. Fusion just has 2 hydrogens, a deuterium and a tritium, smacking to each other really hard, and it makes a helium atom and an excess neutron. So the byproducts of fusion are a gas that is not radioactive, that is super useful because we need helium to power lasers to make every smart device and almost all electronics at this point. And helium's a weird element because it's the only one that can escape our atmosphere without us doing anything. Like, it just naturally escapes because it's so light and so small. And yeah, so it's like a valuable resource. So if we do this, if fusion works, we're going to be generating a byproduct, not nuclear waste, but a very valuable helium. So there's a huge incentive both in sustainability and in economics to get fusion off the ground. So it's pretty neat. Now, I don't, oh good, this animation's actually gonna play. As the fusion hits, you've got the deuterium and the tritium. It shoots out a huge amount of energy and drops off that extra neutron. So beautiful. This one worked perfectly. Oh look, and then the fusion one's gonna work. Okay, fine, whatever, we're just gonna go with it. So here we go. Maybe the other one was just a screen pick or something. Oh, I'll have to check that later. But as you see here, that's the fusion versus the fission. So there you go. This is a stylized picture of the modern nuclear reactor. It has remained relatively unchanged since like the 70s. The principle is very simple. There is a nuclear reaction that goes on deep inside a reactor core. In this, we've got fuel rods, which are uranium-235, which become uranium-236 when they are excited, thus unstable, thus generating crap tons of heat. There are also control rods that just stop the whole thing right there. Inside this large thing called a moderator, and the moderator had various things on it to heat it up, cool it down, or whatnot, and make it a bit safer. In this core, there is the first loop of water. This water gets super, super ridiculously hot, and then that gets pumped into the second set of water. This second set of water is what gets contacted by all that heat and vaporizes. The Chernobyl reactor, we'll talk about that in a second. Let me finish this, then I'll get to that, Aiden. So, because I'm going to show you how it's supposed to work first, then I'll talk about Chernobyl briefly. Anyway, so this second set of water gets superheated, turns into steam, shoots through the tube, and spins a turbine. Almost all electricity is generated this way, of spinning a turbine, generating electricity through its spinning. Solar is the one that does not do that. Pretty much everything else does. Solar is different. We'll talk about that like at the end of the year. So the turbine spins, generates electricity, goes out, and then the water continues on through this second loop. In the third loop, which is attached to a body of water like a reservoir or a lake, and it just pumps in water to cool down the liquid so they can be turned into steam, so it can spin a turbine, so it can cool down, turn into steam, spin a turbine, cool down, turn into steam, spin a turbine, cool down, over and over and over again. So that's that. This is how a nuclear reactor generally works. Now, what happened with Chernobyl was, in short, Russia. Russia happened to Chernobyl. One of the issues with Russia, and China's a little guilty of this too, in fact, it's pretty guilty of this, is safety standards are not seen to. Here in the US, we have very rigorous standards. We actually have higher nuclear standards than most countries in the world. And that's one of the reasons that, our power plants are running quite well because of it. While there was the 3 Mile Island hiccup, they really didn't do that much. I mean, it did release a bunch of radiation, but it went into the atmosphere because all the safety measures worked. In the end, the local people did not really have that much happen to them. The radiation was about 3 summers days worth, which isn't that much. The human body can deal with that for the most case. So there really wasn't a problem. Didn't really kill a lot of animal life or whatnot. But it was a bit scary, the 3 Mile Island. But Chernobyl was a colossal mess up. The biggest thing with Chernobyl is they overworked their staff so that the safety people were exhausted, tired, and relatively brutalized. They used cut rate concrete, which could not contain the reaction when it went critical, and their safety systems were not working, which is why they were doing a safety test, but they kept the reactors going while the test happened. It was just one thing led to another, and a lot of people died, and the area is still irradiated and will be for quite a while. So that's the brief for Chernobyl. There's a beautiful documentary series. Feel free to watch it. It's fantastic. But the short answer to what happened in Chernobyl, Russia happened. The lack of safety standards, the overworking of people, the fact that there was multiple people drunk on shift. Yeah, that happened. So standards are important, and being a professional is also important, especially when you're dealing with something as powerful as the atom. Now, some terms that we need to go over is the reactor is the thing where the reaction actually happens. Fuel rods are a type of uranium that can be, enhanced. Control rods stop the reaction because they suck up all the neutrons, and that stops the reaction from progressing. Moderator controls it by heating it up to speed it up, cooling it down to slow it down, and otherwise monitoring it as well. Shielding, 3 feet of concrete is standard. The U.S. typically uses around 5 because, we don't fool around. Critical mass, well, at least not with nuclear power, mostly. Critical mass is the fuel needed to start. So the chain reaction happens when we reach a critical mass, meaning we have enough fuel for it to go. Water is super important. It carries the heat and the steam spins the turbine. But in the end, neutrons are pretty much the center of this whole fission thing. Now, other radiations. Alpha radiation is useful for smoke detectors, space probes, pacemakers, and things that wipe out static and sensitive equipment. The biggest thing is smoke detectors that you're probably going to encounter in your life. And you can see that's how it generally works. If the smoke shows up, it alters the reflective the light, and as such, you don't get the alarm triggers because, the light bounces off. I'm sorry, I'm thinking of a different version. Beta radiation, treating certain types of cancer. It's a light source, but we're going to talk about carbon dating a little bit later because that's going to be like our main topic. So radiation can be used for a lot of good things as well as bad things. Gamma sterilization, number one most important things. It is the most used form of radiation. So do know this, gamma radiation is the most used form of radiation by humans. Neutron radiation has a whole bunch of neat stuff too, but number one thing here is gamma, most used form of radiation. Super important to know. The state has it as a requirement. You will see that on quizzes, tests, etc. Gamma radiation is what we use. They won't let me have a gamma irradiator here in my classroom. They gave me a UV irradiation thing to sterilize my goggles. And I guess that's okay. And the gamma one is more expensive, but I thought it'd be cool. But whatever. This leads us to the main lesson today. One of the more involved, useful things is half-life. Basically, radiation levels decrease by half over a set amount of time because radiation either yes, it's radioactive or no, it's not radioactive. You have a choice, yes or no, yes or no, yes, no, yes, no, yes, no. As such, when the no's don't go back to becoming yeses. So it's always yes, 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 yes. Now it's no. So this allows us to go, well, if you've only got 2 choices in a certain amount of time, you're going to have an equal amount of no's and yeses for that bit, and that is a half-life. It's how long it takes for half of it to not be radioactive. So that's a half-life. Carbon dating is one of our big examples when it comes to half-life. This is a drop in beta emissions in carbon and allows us to figure out how old organic compounds are. Now, you have to understand that the word organic, it comes from science. It means it's carbon-based, and it is totally misused in like grocery stores and whatnot. And it's kind of okay. It just means now there's like 2 definitions. But we're going to be talking about the chemistry, the proper organic, where if it's organic, it's carbon-based. as opposed to the grocery store organic, which means it uses a different type of fertilizers and whatnot, because don't be fooled, they still use fertilizers. They just use different ones. It tastes good, doesn't taste good, that's up to you. Now, there are many ways to solve these. I'm just going to show you a couple. The number one way I'm going to show you is this hat table. This hat table, sorry about that. Normally there's a joke. I don't care right now. You set it up like this. H is for half-life, A is for amount, T is for time. When you start it off, X-rays is a type of radiation. So when you start it off, and it's very similar to gamma, by the way. Gamma is more powerful than X-rays. We'll get to that when we get to energy. So when you start it off, you've got 0 for half-life and 0 for time, and whatever the amount is from the problem. Every half-life you have, the half-life goes up by 1, 1, 2, 3, 4. The amount gets cut in half. That's the whole point of half-life. And the time goes up based on whatever the material is. And so whatever the material is will increase it. So I don't know why that decided to show up like that. There we go. I'll fix that later. So example number 1, we have this table. Now, I was hoping, very hoping, but it doesn't seem to be working, to use my spiffy little drawing tablet, but it is not behaving. I don't know why it is not behaving. I got it to work earlier. I don't know, maybe it has to do with some interaction with Teams. Maybe that's because Teams is just doing a shell there, but whatnot. Yes, X-rays is a type of electromagnetic radiation as well. It's actually the one that kind of borders the two. Thank you, Jamie, for adding to our discussion. I really do appreciate that. But it's its own type of electromagnetic radiation. I'm wondering if there's a different way I can do this. Maybe I can share my screen. Yes, I can share my screen. So we're going to do that instead. Okay, real quick, raise your hand. Can you now see the thing at uses? Can you now see my screen showing the word uses and a picture? I am not seeing anybody who is raising their hand, so I'm assuming that this experiment failed, that you cannot see the new share.
We can see that people are raising their hands.
Oh, okay. Why? Then Teams is just being annoying. Thank you very much for whoever started talking. Who was that, by the way?
That was me, Logan.
Logan? Okay, got it. Logan raised his, Logan said that. Thank you, Logan. I appreciate that. It was not showing me you were raising your hands. What the heck is going? Oh, I know what's going on with Teams. Oh, I freaking hate this. Okay, so for your knowledge, students, Microsoft is majorly updating all of its stuff to try to get ready for the school year that's already begun for almost everybody. Unfortunately, they're doing that in stages, and Teams being connected to everything is the thing that's affected the most. So in other words, we're going to have to deal with various issues as time goes on. Okay, but let's see if this will work properly, because I really wanted to do this in stages. Okay, so can you see me scribbling? Somebody say it. Logan, yes. Can you say it?
Yeah.
Yeah.
Okay, good. Okay, sweet. Thank you all. Oh, I'm happy to hear so many voices. Okay, so basically it goes like this. I have a drawing pad, and I'm going to be using this extensively, and it's supposed to work in Teams, but it's not working in Teams that way at the moment. So here we go. Okay, so for a half-life question, you have got several bits of information here. The first bit of information that I am going to be discussing is that whole time thing. So when we have time, time is based off of whatever the substance is. So this here is carbon-14, which is radioactive carbon, and carbon-14 is 5,730 years. So whatever the substance is sets the time that it takes for half-life. So I'm mouse drawing at the moment. I don't know why I'm doing that. That's kind of dumb. I have my drawing pad. So carbon-14 has that half-life. Okay, so that is going to be our time. So were I to sit there, like since this is one of the first times that you'd be doing this, I highly recommend that in the time section, you just make a note to yourself that that is the time that we are going to be using. Similar notes, by the way, would be half-lives. I just put that at half, or sorry, amount is half, and half-lives are +1. So this is what I'm going to be doing at each of these sections. Now, really critical whenever we do half-life questions is that we start with our half-life as a 0 and our time as a 0. This is like the #1 thing that is missed. Is having half-life and time be 0. Now, the amount you're going to get whatever the problem tells you. So in this case, the problem is telling us that we have 100 grams as our amount. All right. So 100 grams, write the whole thing. All right, so that's how we start. Now, what we do then is we look at the question. We've got our start right here, and we have this thing here. This here is our stop. So the start, then the stop. You will have a start and stop at each problem. We start with the start and we go till we get to the stop. I know that may have sounded simplistic, but there's a method to my madness. What this is then, we take whatever column the stop is in and we just solve that column first. So I'm going to have this 250, 225, then it's going to go to, oh, that's how I get the eraser. That's nifty. To 12.5, and all of these are in grams. And I want to get to 6.25. Oh, good. That's going to be my next one. 6.25. Okay. So that's as far as I'm going to go. It's just going to go to that. So that's how I deal with how far I go. Because if you went further, then you'd have to have more and more lines as it goes down. But there it is. So as we go, we start at the 100, then half, 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 half until we hit our stop. Then we can go back to the problem and go, okay, the half-life is 1, 2, 3, 4, because sometimes it's going to want us to say it. Now the time, we're going to be adding this time. So the first time is 5,730, and I'm just going to keep adding that. I'm going to just add time over and over to this, and this would help if I had my calculator handy. And I believe the next one is 17190. And again, all I'm doing is I am hitting plus 5730 each time. Sometimes you accidentally hit the multiplication sign and then you're like, fudge, and then you go from there. Okay. I need to move my little Teams notification thing because it gets in the way. So 22920. Okay, now this is in years and this is my raw. Okay, because again, we need to go back to the question and we need to look at the numbers it gives us. I've got 3 sig digs, 3 sig digs, 3 sig digs, which means this goes to 3 sig digs and the 2 does not round up the 9. So my final answer is going to be 22900. You cannot see the bottom bar. Oh, really? That is annoying. Okay, well, let's check something then before I go any further there. And thank you very much for whoever is, for all the people who are posting. Can you see all of this? Please give me a shout out because it's not letting me see you raise your hand.
I can see it.
Can you see the 22900?
Yeah.
Okay, good. Okay, so the other one for some reason wasn't letting you see the bottom. This is cool. This is
I saw
our
the bottom
answer.
on the other one.
Oh, okay. Well, then whoever couldn't see the bottom, it may be on your end then. All right, thank you, Logan, and thank you other people for commenting. So this here, this is our final answer, sig dig. Now we need to have a quick discussion on sig digs, which is just going to take a moment. Now that we are in chapter 2, I'm going to be easing up on sig digs a bit. You're going to be allowed 1 difference of sig dig for full credit, meaning this question has 3 sig digs from the problem. But if you did the raw answer of 22920, that has 4 sig digs, which I will accept at full credit. The AP students figured out that you can kind of cheat sig dig wise with that rule by making everything 3 sig digs, because almost everything a teacher gives you is going to be 4, 3, or 2 sig digs. So you should just do 3 if you have the 1 leeway. So if you're ever confused on sig digs, use 3. This is going to make some of the math problems I put in a little more tricky for me to put together, but hey, it's life. That's how it is. Now, the other way to do half-life questions that works out well is logic. Logic can be used, but logic changes for every single problem. So for this example here, what I would do logic-wise is I go, okay, I'm just going to keep dividing this by half until I get to what I need. So I divide it by half once, twice, thrice, 4 times, meaning there were 4 half-lives it took to get from full, so from start to stop, from full to my final. I then multiply that 4 by the years for half-life, and then bam, I get my raw, and then I round to my sig dig. This may seem easier, but remember, I'm the one who did it. You have to do it different every time, which is why I highly recommend you learn the table, because the table is done the same way each time. Now, it's on you though. I'm basically never going to see which way you do. I'm just trying to help you out. For those of you who end up taking, I think it's geology, if you ever take that in another year, they use this again. And if you know how to do the table, it makes all those types of problems easier. There's also a formula you can use, but it involves changing exponents, and that's just a headache. So I don't like ever use that. Logic works, the table works, use what you want. The table is better for most people. Now, real quick, what I'd like you to do, there's this practice question. Oop, yeah, I just flashed the answer, but that's fine. I'm going to give you just a couple minutes to try this, whether you use logic or whether you use the table. Oh, and I'm going to want you to consider this as 300 dot. I meant to change that and I forgot. I'm literally just going to give you a couple minutes to try this. We're only going to do this a couple times in this class, but this is going to be one of them, because normally I like to, fill your time with me talking. So like I said, setting my timer. We're just going to have a couple minutes for you to try this. If you're like, Mr. D, I just want to hear you talk. I don't want to do anything. I'll do things when this is all over. That's fine too. I guess you can take a 2-minute bathroom break, but I would prefer you try this, because, that's how you know that you're doing it well. And if you bump into any problems, you can ask me. So I'm going to let you try that for a pair of minutes, and we're going to go from there. A few of you have also figured out if you download the thing, you can just skip ahead and see the answer, but that's not the point. The point is, can you do the process? There are very few answers I want from you. I want process. I want you to learn how to think, how to solve, how to do the various things that will help you get the right answer, more than I actually care about the answer. And this is a thing that pretty much goes all year. Because in the end, no one question here in chemistry is going to be like the thing that defines what happens. But maybe you understanding how a problem works can make your life a lot easier later. Understanding how to do this may open up new job opportunities. I've had people use things in my chem class to start careers, careers that they now have, that they're successful, they're happy, and all because of something that they learned in my chem class. Pretty happy about that. So it's the process is what I really care about. You're thinking. I also really stink at shutting up. So I'm sorry if I'm distracting you. Just 10 seconds remaining for those of you who are working. I'll give more timer warnings next time. Still getting used to this. Okay, so here's the deal. You set up your table like you normally do, half-life 0 times 0, and then you build the problems like so. Now in this case, we got all the way to 5 half-lives is what it took to get from 300 to 9.75 grams. And that here is the raw answer. Now, if we look at this, we should be setting this to 3 sig digs, so it should be 28700, but we're allowed to be off by 1, so it's not a big deal if you just leave it raw of 28650, and that'll happen a lot. So there you go. That was your practice for that. Now, we can also make it so that we're looking at time and instead of amount. We also can look at half-life instead of time and amount, but this is different. So again, you can look at my note to the side. It doesn't matter which is missing. All of this is solved the same way, which is why I love the table method. So we're going to make our table, and we're going to start it off like we always do with our time of 0 and our half-life of 0. So half-life 0 times 0. We are dealing with strontium 90 now, so we are going to have a new time requirement. Okay, our time is now going to be 28.8 years. All right, so that's going to be our new time, 28.8 years. Okay. We are going to remember our samples. We're going to have it, and our half-lives, we're going to add 1. Now, in this case, we have 2 times 1 amount, because our stop is not amount. Our stop this time is time. So this is our starting amount, our 500 grams of sample, which again, we want to write in amount. But we're not stopping at this column. We're stopping at another column. And the column we're stopping with is we're stopping at time. So I'm going to do time first because that's where our stop is. This will help me figure out how many of these lines I have. Now, of course, I pre-programmed this in, so I'm pretty certain it stops at the lines that I have there. But just in case, I mean, you may not know that. Okay, also I gotta change this. This pen is really sensitive. Okay, and plus 28.8. And then we just, oh yeah, okay, cool. So no, I don't need the last one, because as I get to here, I've got 86.4. Now, a lot of times people will mess up and they'll double this column. No, that's not how that works. You just add the time each time. Start with 0, then you add until you run out. So there's our stop. So I don't need to even do anything else. I don't need that fifth line down there. And then this is going to be 125, and this is going to be 62.5, and this is going to be in grams, and then half-life is 1, 2, 3. Some questions do ask for half-life, which is why it matters. Now, again, this is on me. I meant to put a dot there for it to be 3 sig digs. If it was 1 sig digs, your answer would be 60 grams. If it was 3 sig digs, it'd be 62.5. And I will be trying to make sure that these are all set properly. For some reason, I don't know why, but the sig digs on the half-life problems are a little wonky. So I need to go and adjust how that happens. Okay, now we can also use logic, but again, it's going to be done completely differently. We're doing this in a different order. So I take my years, I divide by years to get half-lives. Then I just take the half-life, divide, and I get an answer, which happens to also be my answer. Sig digged. Notice this one's got the dot. See, look at that. This one's fixed. Whatever. So whether you have a complete table or you have logic, that's how you do it. And it doesn't matter what column you begin with, especially if you do the table, it's done the same way. The last hiccup that we have here is reverse. If I go in reverse, that's a bit tricky because notice it's giving us back in time. How big was an original sample? There's a lot of ways to do this. My recommendation, the way I like to do this is I like to do my table as normal. My half-life is 0. My time is 0. My amount, I do not know. That is what I'm looking for this time. So that is what I am trying to find out. And at this point, again, you've got 2 times. And since your time is at 2.1 minutes, So again, that is your time, 2.1, and that's minutes. Amount, again, we're going to divide by 2, and half-life we're going to add 1 is typically how the column goes. So I'm going to take my time section, and I'm going to do that one because that's where my stop is. So in this case, I have the amount is blank because that's what I'm trying to find. So I do my 2.1, 4.2, 6.3, 8.4, and then 10.5 minutes. And that there is my stop. See, there it is. So that says here there was 0.12 grams. And our half-lives are 1, 2, 3, 4, and 5. Okay. So now what do? Well, if we normally go half down, what we're going to do is we're going to do the reverse. We're going to multiply it by 2 going up. So in this case, since we're going up, we're going to times it by 2 as opposed to divide it by 2. Again, this is just how it works easiest for me. There are other ways to do it, even using the table. It is largely up to you. But the key thing is to have a decent amount. I'm pretty certain. Look, it's early in the morning. I'm going to make sure I do this properly and not write down a wrong number here. So I'm switching to my calculator real quick. Okay, good. I know that's the answer. 3.84 grams. This is my answer. Now, again, we've only got 2 sig digs here. So it should be 3.8 grams is going to be my final answer here. But again, we're allowed to have 1 leeway for sig digs. So the 3.84 would work as well. Now, that said, and I know I haven't been like having you raise your hands repeatedly through this, and that's just because, you know, it's been kind of heavy. If we did this logically, it goes like this. I figure out how many half-lives. I then multiply by those number of half-lives. I get my answer. So, you know, logic does work. It's just, and it can even be quicker. It just changes with every problem. And I don't know about you. I don't always like it when my problems change all the freaking time. So that's why I don't always recommend it. Oh, good. I'm glad, Eden, that you had figured out how that works. Okay, so here we go. We are now at the end of our lesson. Half-life is the big deal here. Haley, do you have a question? No? Okay. In that case, if you have a question, feel free to raise your, oh, sorry. Whoa, hold up. Hi, I almost forgot something. Tomorrow, you're not going to see me. If for some reason you need to do a Teams meeting or whatnot, this is an excellent time to get a hold of me because I'm normally just grading and prepping things for you all. So you can shoot me an email. Hey, Mr. D, can we have a quick Teams meeting to discuss X or Y? So on our off days, feel free to do that and I might be able to help you out. Otherwise, on Friday is largely going to be a Q&A session. I am going to try to play Quizlet with you, so we're going to see if that works. It might end up being a dumpster fire, but hey, you know, I want to see if that can happen. So I'll be trying that out. But in any case, I bid you a good day. We talked about uses, we talked about half-lives. That should be one of the last things we do this week. So next couple days, just focus on getting your work done, catch up on anything you're missing, and we're good. If you have any questions, put it in chat or send me an email, but I got a bunch of kids waiting out there and I'm gonna have to let them in at some point. So toodles, take care. Talk to you all in 2 days. Thanks for coming by. And this time I remembered to record attendance, so I'm pretty happy about that. I'm going to make sure that attendance document actually downloaded though, because last time it lied to me. It said it downloaded, but it didn't. I am really hoping that that stops. Okay, good. It did download. Now, can I open it? Or is it also logging to me? All right, let's stop that recording.